And we had kind of come to the conclusion, I hope, I had tried to get you to come to the conclusion that whenever you've got a product of a polynomial and a transcendental, just like this one, but the transcendental is ln, it needs to be set up in a very specific way, right? That's kind of where we finished last time. So the specific way is the u has to be the ln, because we can find its derivative quite easily. If you make the dv ln, it's going to be a bigger problem, a significantly bigger problem, because at this point, we don't know the antiderivative of ln. So we would make u ln of x and dv x squared dx, and then we'd go from there. So this is a good takeoff point? What?
He was trying to take the wrapper.
Oh, okay. Recorded forever, right here. So it sounded really desperate. Like, please, no, please. Okay, anyways, back to this. So once you set this up right, it comes down to doing the whole ultraviolet voodoo. Don't forget that voodoo is bad, so it's negative. And so we would just say uv, I'll probably write it in the other order here, 1/3 x cubed ln of x minus the integral of voodoo. So that would be 1/3 x cubed times 1 over x dx. You can see that the x cubed would cancel with the x a little bit, so you'd end up with 1/3 x cubed natural log of x minus 1/3 integral of x squared dx after you do that canceling with the x cubed and the x. And once you boil it down to this point, of course, it's just a very simple power rule, right? And we're done. So it'd be 1/3 x cubed natural log of x minus 1/9 x cubed plus c. Okay, so again, just a special note, if your u dv, your original, has an ln, make your u ln and dv just be the other stuff. That's how it's going to work out best. Okay? All right, well, let's take a look then at example number 3. Assuming that you're doing good with remembering a little bit, I think example number 3 would be kind of the first one where I'm going to say, just try it on your own, see how it goes for you. Try to pick the right u and dv and all that good stuff, and then we'll check your answer in a couple of minutes. And we'll get some input from you guys as to what we do with that. So in a case like this, make your u equal to x and make your dv equal to the other stuff. So if that is the case, Caleb, what's your du? 1 dx. Yeah. We're doing differential. So yeah, 1 dx, or we could just write dx. All right, and then Caleb, what is your v? If your dv is
e to the x.
E to the x. Yep, you got it. Okay. Whoops. So then, Sean, what do we do with that information? Like, how do we set that up?
uv. So that is equal to uv minus.
Okay, so you want me to just multiply the u's and the v's, the u and the v. So x e to the x.
X minus integral e to the x dx.
That's right. Okay, and so this actually finishes pretty quickly now, doesn't it? Because the antiderivative of e to the x dx is just e to the x, so we end up with x e to the x minus e to the x plus c. Okay, any questions? Okay, so let me at least introduce number 4 for you. With number 4, the little rule I mentioned before about if you got the polynomial and the transcendental, as long as the transcendental isn't ln, always make your u the polynomial. So with this one, like your initial setup, really should be, kind of has to be, u equals x cubed and dv is equal to cosine of x dx. It really has to be like that. Of course, some of you have started to look at this one. It doesn't just like finish real clean, does it? There's like more there. So I'll let you kind of run with that and maybe try to come to a conclusion. And then if you look ahead, you can see example 4. Oh, sorry, it says example 4 could be more easily done with a different method. So I do want you to go through example 3 to show you can, like, this mechanically can be done, but then I want to show you example 4, and I don't know, you could call it a shortcut. It's good though. Oh, nice. Oh, did that not go? So close. Let's do this here real quick, and let's at least compare answers, make sure we all agree. So if we set this up the way that we have, we end up with du equaling 3x squared dx and v equaling sine of x. Oh, sorry. There we go. So you set up the ultraviolet voodoo thing, and you end up with x cubed sine of x minus the integral of 3x squared sine of x dx. And of course, you look at that integrand and you think to yourself, oh my gosh, that's another integration by parts, like it's another polynomial times the transcendental. And so you might feel like that we've made the wrong choice, but notice how the degree on the polynomial went from 3 to 2. So that's a good pattern, right? We want it to go 3, 2, 1, 0. And if we can get it down to where it needs to go, then we'll be done. So this actually will finish. We're just going to need to apply the process a couple of times. What I'm going to do here, I'm going to write my answer down below, but I will switch colors just so we can kind of distinguish here. So I'm just working on this integrand this time. So I got a new u, so my u is going to be 3x squared. So my du will be 6x dx. My dv then has to be all the other stuff, so sine of x dx. V then equals negative cosine of x, and I can reset up a new integration by parts. And I'm going to try to keep track of all this by colors. So I'm going to write x cubed sine of x, that's from up here, minus, and then I'm going to write this other stuff in red. So I'm going to put it in parentheses. It's going to be minus ultraviolet voodoo, so it's going to be negative 3x squared cosine of x minus the integral of voodoo, so that would be negative 6x cosine of x dx. Does that make sense? Okay, now I'll clean it up a little bit. I'll make it x cubed sine of x plus 3x squared cosine of x. And with all those minuses, there's really 3 of them because there's the green minus and then the 2 red minuses. It'll be minus the integral of 6x cosine of x dx. Okay, still hanging in? Okay. So good news is we're almost there. I'm getting pretty close. I'm going to switch colors again for this next step. So I'm going to write, well, actually I'm going to write in red. Let's see here. So we're going to have x cubed sine of x minus 3x squared cosine of x minus, and then I'm going to put this in a slightly different color here. We'll go with this, 6x cosine of x dx, and I'll do ultraviolet voodoo with the blue integral, right? Because again, I've got a polynomial times a transcendental. So I'm going to go with u equaling 6x. Therefore, du is equal to 6 dx. dv then would have to be cosine of x dx, and v would have to be sine of x. And we can see it's actually going to come to an end now, isn't it? Because my voodoo is going to just be 6 sine of x, which is not another integration by parts. That make sense? So here goes. Here are my first 2 terms left over. X cubed sine of x minus 3x squared cosine of x minus, and then I've got my integration by parts here, so this is going to be ultraviolet 6x sine of x minus voodoo 6 sine of x dx. There we go. And so now we can just finish this off. So I think I can go straight to a final answer here. My final answer in the end is going to be x cubed sine of x minus 3x squared cosine of x. That minus sign will get distributed, so it's going to be minus 6x sine of x. So the antiderivative of sine is negative cosine, right? So it's going to be minus a negative cosine. So in the end, I think it's going to be minus, right? So it'd be minus 6 cosine of x plus c. Oh, what do you see?
You lost your plus sign from bottom left where the x cubed sine of 3x or sine of x plus.
You know what I
3x
did?
squared.
When I rewrote it, I was looking at it like this. I just didn't even see it. So that's easy to fix. So that's plus, right? There we go. Okay. I zoomed too far and my memory left me. Okay, so, oh, my plus c got chopped off there too. You guys good with that answer? Are you good with the process? Are you happy with the process? There's got to be a better way. You've seen it coming up. So, let's do this. And I think you guys have the answer written down on your paper. I'm gonna get rid of it here. And I think I might have a chance to show you a movie clip at the end. This will be fun. Okay, so tabular integration. Whenever you have to do repeated processes of integration by parts, in my opinion, this tabular method is best for sure. So here's how you do this. Let's remember the original was integral of x cubed times cosine of x dx. And so here's what we do to set this up. I'm basically going to make a little table. That's why it's called tabular table, right? Integration. And so this table is going to be tall and skinny, something like this. I usually put a little ddx at the top just to remind myself, and believe it or not, it's pretty easy to forget this. ddx at the top reminding myself to differentiate in the left column, and an integral on the right reminding me to do the antiderivative in the right column. In these situations, just like we set up with our ultraviolet voodoo thing, I want my polynomial to start off in the ddx column and the other junk to start off in the other column. And so here's how we do this. I'm going to put x cubed right here, and I'll put cosine of x over there. And I'm just going to build my column out. So here's how I do that. On the left side, I'm just going to differentiate repeatedly on down the column. So it'd be 3x squared, then 6x, then finally 6. And of course, the next derivative would be 0, but we never actually have to go to a 0. And then on the right-hand column, we do our antiderivative. So this is where it's easy to mix it up, like because we might accidentally do a derivative going down. So maybe make a little note to help yourself. Remember that you're doing an antiderivative over there. What is the antiderivative of cosine? Correct. And then we continue on with the antiderivative of sine. Negative cosine. And then the antiderivative of negative cosine would be negative sine. And we actually have to do one more level in this column. So what's the antiderivative of negative sine? Cosine. Correct. Okay. And so then the final thing we need to do is this. I'll do this in a different color. Hopefully it'll stand out to you. Is off to the left here, we're going to put plus, minus, plus, minus. It always goes in that pattern if you set this up correctly. This is just a little algorithm to make this go quickly. And then here's how you get your answer. You connect on diagonals. You essentially multiply on diagonals. So the answer would be x cubed sine of x. And then in that next diagonal, you're going to get a negative times a negative, which will be a positive. So plus 3x squared cosine of x. The next diagonal is a positive times a negative, so it'll be a minus 6x sine of x. And then the last diagonal multiplication is a negative times a positive, so minus 6 cosine of x, and then plus c.
Yes.
So basically you set it up, you just carefully do your derivatives and antiderivatives and just go diagonal, boom, 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 deal with the signs and you're done. So you can obviously see that took us, even including the setup, like maybe 2 minutes versus the other one. There's like minus signs everywhere with parentheses, and I unwittingly like forgot a minus sign because I like looked at a different, I didn't look at that part of my paper. I mean, that was unintended. You can see it's easy to make like a little tiny mistake that'll end up being a frustrating one because you shouldn't have done that. This, to me, is easier for the repeated processes. So I was telling Darian earlier, like if it wasn't integral of x cubed cosine of x, if it was like integral of x to the 20th cosine of x, tabular integration really wouldn't take that much longer. It would take more space. It wouldn't take that much longer. Integration by parts? Like you'd need like the width of the board, wouldn't you? You'd need like a really large piece of paper to try to fit all that in there. This would be over with. I bet you could do, I bet you if you had to, if it was x to the 20th times cosine of x, you could probably get that done in less than 10 minutes and be like 99% sure it was right. Not with integration by parts, right? I mean, seriously, x to the 20th, as long as you got a calculator, you can do like 20 times 19 and blah, blah, blah. Numbers will get huge, but it's doable. The other way, time is a little bit prohibitive. Yes, ma'am?
So how do you know when it's best to use it?
So yeah, so I think that's a matter of opinion. So for me, I would, like my dividing line is pretty low. Like I would say if the polynomial is x, if it's x, I'm definitely doing ultraviolet voodoo because I can just go ultraviolet voodoo done. If it's x squared, I could go either way. If it's x cubed, there's no doubt I'm doing this. Anything above that, there's no doubt I'm doing this. X squared, I probably would do tabular also. I mean, you just go x squared, 2x, 2, boom, 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 diagonal, 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 done. I mean, it would be over with pretty fast. So anyway, that make sense? Okay, awesome. Well, let me close you off here. We're done at 50, correct?
Yeah.
Okay. Let me close you off with a little